This is the 2016 scholarship exam question 2. We got vibrating waves. So long wires stretched between 2 points can vibrate when a steady wind blows past them. Engineers in dealing with these problems caused by these vibrations have found it useful to define the Strahul number, ST as ST equals F times R over VW. F's frequency, R's radius, and VW's a wave speed. Show that the Strahul number is dimensionless. So all we do is we'll just write ST is equal to F over VW, and then we'll write that as units. So frequency is just 1 over S, it's cycles per second. And that is times, radius is in meters, and then velocity is just meters per second, which is essentially equal to 1 over S times M times S over M. And then you can see that the S's cancel and the M's cancel, and that equals 1, which is just dimensionless. Dimensionless. LASS. I don't actually think ESS. There you go. Cool. Right. Next question. We have a window washer cradle with 4 meter width is suspended from 2 cables of equal length. A steady wind of 10 meters per second causes the cables to vibrate with frequency 200 hertz. In this situation, the Strahul number is 0.2. Of 0.2 is typical. The wave speed and the wire is given as V equals square root T over the mass per unit length. Oh no, is it mass per? Yeah. Mu is a mass per unit length. T is a tension. Just covered there. Explain using physical principles why the wave speed in the wire depends on the tension and the mass per unit length. So I'll go with the mass per unit length first because it's a little bit easier. Lighter masses for the same force will accelerate more. Did that just make sense in my head? Yeah, it did. So something that's a lighter mass will accelerate more under the same force. So that means they'll accelerate more, hit another one, hit like another particle. It'll accelerate more, hit another particle. So the speed of the transmitting wave is faster, and then tension means the intermolecular bonds between the particles. If the tension is higher, it means if one jiggles, the other one is gonna jiggle like the same. I don't even describe it. What's a physical? I think what a good example of it is. I can't think of any like real. I just know that like the tension, the higher the tension, the faster the wave is going to travel through it. I think I'll just pause and think of a good analogy. I think I was explaining it wrong. Tension is just the force. So if the force on the particle is higher, that means the acceleration will be higher. So yeah, so you're just looking at it like that way. So I'll pause and try and write out a semi-coherent answer. Right, so I said the tension is the force acting on the particles. Greater forces lead to greater accelerations, meaning increased wave speed. Mu, which is the mass per unit length, affects the wave speed, such as VW, via the mass. Less mass per unit length means greater acceleration for the same force, leading to greater wave speed. So those are 2 ways that can affect it. I didn't really do a great job of answering that question. Right. The cradle has a mass of 100 kilograms, and the window washer who's standing in the middle of the cradle has a mass of 75 kilograms, including mop and bucket. Given that the density of the cable is that, show that the wave speed in the cables is 18 meters per second. Right, so we've got the velocity formula from over the page. V equals square root the tension over the mass per unit length. First thing we'll do is find the tension. So the tension is just equal to Fg, which is equal to mg over 2, because there's 2 cables. So we're just going to find the tension of 1 cable. That's why I just chucked that 2 in there. I'm just sort of talking it through as opposed to writing it through. So that is 175 times 9.81 divided by 2, and that is equal to 858.4 newtons. I've already done this question because scholarship questions take me a while to do calculations for. That's why I always pre-do them, and they're hard as well. So mu is essentially mass per unit length. So I'll just call it unit L, which is essentially, in terms of units, kg per meters. Right, so what I need to do is I need to find out how many kgs in a meter of the wire. And we're going to just write down the definition for density, because we've got that. So density is kgs per meters cubed. So I write the units first, and then I go from the formula for there, which is equal to mass over volume. And just a little thing. So, in other words, mass, because I basically want to find the mass, and then if I divide by 1, I'll have mass per unit length, so kgs per 1 meter. So mass is essentially equal to the density times the volume, which is equal to the density times pi r squared. I don't know what r is. What the heck is r? They don't give us r, but they give us this formula up here with r in it. So we'll rearrange that. So we'd move the VW up and the F under. So we're going to have, and that would be pi r squared. So we're going to have, what is it? The Strahul number, VW over the frequency, which is, and this is r. That's squared, and we'll times it by the length of 1 meter. So let's call this L, but it's just going to be 1 meter, and that is going to be equal to, so the density is 8 times 10 to the 3 times pi times the Strahul number. I'm pretty sure they gave it to us, 0.2 there, and 200 hertz as well. So we're going to have, and I think the wave speed was 10 meters per second. Yeah, it says it down here. Right, so we're going to have 0.2 times 10, over 200. We're going to square that. We're going to times this by 1 meter, because it's the mass per unit length for 1 meter. And that equals 2.51 kgs per 1 meter, but I'm just going to get rid of the 1. So it's just kgs per meter. Now we're pretty much done. So this is essentially the mass per unit length. So we have V is equal to square root. The tension was 858. Yes, it is. 0.4 divided by 2.51. Hope we can see that. We totally can. And that is going to be equal to 18.48 meters per second negative 1, because it's a velocity, and it said show it's 18, so we have shown thus that velocity is 18 meters per second. Cool. The window washer moves from the center of the cradle to position 1 meter from the center. Compare the wavelengths of the vibrations in the two cables. So I'll draw a quick little diagram. I've got my ruler with me. So we're going to draw a little diagram, and here's the cradle. And we have, call this one T2, we'll call this one T1. The little man is 1 meter from the end, and the whole thing is 4 meters long. And we'll chuck a little man in there, because why not? I hope you can see the little man. Right, so we have to use torques to find out the force on T2. So T2 would have a tension force pointing upwards, so that would make it spin anti-clockwise. The little man would have a gravitational force pointing downwards, so that'll be a clockwise torque. Clockwise torque. So we have anti-clockwise torques equal to clockwise torques. I'm just going to write the actual equations. We're going to have M, and this is going to be our pivot point right here. So here's our pivot point. In other words, mg times, how far away is he? 3 is equal to, so this is a force times the distance, is equal to the T2 times, how far away? 4. Yes, because he's 4 meters away. In other words, T2 is equal to 3/4 mg. Thus, T1 must have the other quarter. I mean, someone's got to carry the other part of the dude. So he must have, the tension of the first one is going to have quarter. And the reason why I'm just talking the dude is because the platform's still evenly spread. So we'll tack that on at the end. In other words, T2 is equal to, what's it equal to? 50, because it's going to carry half the weight of the platform, times 9.8, 1, because it's level 3, not level 2, plus, which one's T2? 3/4, 3 over 4 times, what's the mass of the dude? 75, times 9.81, and T2 equals, what's T2 equal? I wrote that down before, 10, 42.3 newtons. Same applies for T1. I'm not going to... T1 is just this number plus quarter mg. I mean, you can do that yourself. That is going to be equal to 674.44 newtons. Right, so now, because what I want to do is, I know the velocity formula, and I know, so we know the wave equation, V equals F lambda. I'll just check that over here, V equals F lambda. I know what the frequency is, it's 200, it says over the page, so it's going to be constant. 200 hasn't changed because the radius hasn't changed, the wave speed hasn't changed, and the Strahul number hasn't changed. So, yeah, and the wave speed is, the wind speed, not wave speed. Why do I keep calling it the wave speed? It's a wind speed, VW for wind speed. It's because that VW is used for wave speed when you're doing Doppler shift. Right, so we're going to have V1 would have equaled square root tension over the mass per unit length. Mass per unit length hasn't changed to 2.51. I've already done the calculations off paper, so I'm just going to skip that to save time. 20.36 meters per second -1, and V2 is equal to, that would have been the square root of 1042 divided by the mass per unit length, so it should be, hold up, V1, 16.381 meters per second. I'll just do the sniff test because that seems a bit shoddy. V1 has less tension, thus it has a higher velocity. That doesn't seem right. How could something with less tension have the higher velocity? I think I've muddled something up somewhere. I totally had. I quickly checked T2. This is T2. This is V2. And this is V1. That's why. Yeah, it pays to just do like a sniff test when you're doing these things. I wrote it down on a page further up. That's why I muddled it up. So, lambda 1 is equal to V1 over F, which is going to be equal to 20.36 divided by 200, which is equal to 0.102 meters, and lambda 2 is equal to V2, which is the slower velocity, F. I hope we can see that, and that is equal to 16.381 over 200 equals 0.082 meters. That's it. So I've compared them. Thus compared. Right. Last question. Oh, we're pretty good for time. In this scenario, the window washer does not hear beats. Explain the physical conditions required for him to hear beats from the vibrations in the wires when he's standing in the window washer cradle. I mean, does he not hear beats? No, because frequency is just 200. Says right here, frequency is 200, and it relies on this formula up here. So we'll just say what beats are. Beats are when you have two similar frequencies, and the waves go in and out of phase. Well, they do. They go in and out of phase, and the difference in frequencies gives you the beat frequency. So if you've got like 80 hertz and 100 hertz, the waves, the 80 hertz frequency, or the 80 hertz source and the 100 hertz source, they go in and out of phase, and you get a 20 hertz beat frequency because it's literally just a difference. So I'll just pause it, and we're going to use, so F, I'll just check the formula, F beat, I don't know how to spell that, is equal to magnitude of F1 minus F2, that was absolute value, and that's frequency from over the page is equal to STVW over R, so is equal to the Strahul number, wave speed, yeah, VW, wind velocity, not wave speed, God, I keep on forgetting that, there we go. So how do we change the frequency? We could change the Strahul number, but I don't think we can because I actually know what that even relies on. The wind speed, well, we could shelter one of the wires so it doesn't get as much wind on it as the other, or we could change the radius, which would be a whole lot easier. So I'll pause and write up a coherent answer and then go over it. Right, so I've said in order to hear beats, there must be two similar but not identical frequencies playing. Frequency depends on the Strahul number, the radius, or the wind speed. So either change one of the wires' radius, it's probably the easiest thing to do, or shelter one of the wires from the wind a bit. I mean, you could sort of block one of the wires somehow, so it's not as windy. Probably not as easy as changing the radius. Sweet as, that's it.